My background is a biology teacher. I used to teach biology in a secondary school. So I used to teach about the brain before we knew as much about the brain as we know now, but certainly a bit about how it works and so on. But I don't want this to turn into a biology lesson, so if there's too much biology, wave your hand and tell me that I'm going over the top. So this is what's in the program that it says I'm going to talk about. Critical consideration about how findings from neuroscience research can be applied in the classroom, appropriate and inappropriate applications, thinking through some implications, and also how some existing psychological theories of learning that have been around for a long time, how they fit with some of this neuroscience research that's now coming out. And I don't know whether you've come across this term neuromyth before, but the idea that actually some of these things are being presented as though they are grounded in really sound neuroscience, but actually they're not. They're myths. They're fictional. How do we know about the brain? Well, lots of sources of evidence available to us these days. One rather cynical person said that the invention that enabled us to know most about the brain, how the brain worked, was the motor car. Why? Because once the motor car was invented and people started driving around in cars, they had accidents and their heads were damaged because they didn't have seat belts. And by seeing what the effect was on different parts of the brain of damage to the brain, then you could make some deductions about what those parts actually did. But certainly disease, we know brain tumours and other growths in the brain, how they affect personality, how they affect cognition, thinking. All those things contributed originally to our sort of understanding. So surgery, what happens if parts of the brain are removed. Direct observation. You can put electrodes on your top of your head and you can measure or detect brain activity. The EEG device is something that will do that, and that's been around for a long time. And we can gain some understanding about which areas of the brain are actually in operation from that, but it's only on the outside. What's really made the difference are all these techniques like magnetic resonance imaging, MRI, scanning. I'm sure you're familiar with things like the picture at the top, which can show you things like the picture at the bottom, areas of the brain, either showing activity in terms of blood flow. In fact, mostly it's showing you how blood is flowing to the brain and drawing a conclusion that if there's blood flowing to that part of the brain, that part of the brain is active. So we're seeing in 3 dimensions, in cross-section, what different areas of the brain do. The other area is spectrometry. And I think this is quite interesting in terms of, in the past we thought of the brain as an electrical organ. Not an electric organ, that's something different, isn't it? But an electrical organ. Now we're thinking of the brain as an electrochemical organ. And there are lots of chemicals in the brain which we understand affect its function and have quite significant effects at different times in our lives on what the brain is doing and how we think and how we can use it. So we've got lots and lots of evidence coming in from different sources. This is the biology bit. I'm sure this sort of diagram will be familiar to you from studying biology at school. It's just a typical nerve cell. The only reason for looking at this now is to just make the point that this is the structure of a nerve cell. There are billions of nerve cells in your brain, but they all have the same basic structure. And they're just like any other cell in your body. They have a nucleus, which is the bit that controls the cell in the middle, a cell body. The difference with a neuron, most neurons have a projection. So I didn't ask, are there any biology teachers in the group? Right, that's interesting. Thank you very much. If I get anything wrong, please tell me. So projection from one side of most neurons' nerve cells, called an axon. And that's the thing, that can be quite long. I mean, some axons are not the whole length of the body, but they are quite long structures from one tiny little cell body at the end through to the terminals, as it says there, or the dendrites is another word that comes up here. And I will just draw your attention to, in the axon, this myelin sheath. You might not think, well, this isn't very important, but actually it is. Myelin is a protein, and if a nerve axon in a nerve cell is coated with myelin, it's able to conduct impulses much more quickly than if it doesn't have a myelin coating. So the process of what's called myelination, acquiring the myelin coat, is actually significant. And I'll come back to that point later on and see whether you've remembered what I've said now. So that's just the basic sort of biology of a nerve cell. Nerve impulses are transmitted from one nerve cell to another, from those dendrites at one end through to the terminals at the other end. And the transmission across to the next nerve cell, I haven't got a diagram here, involves a nerve impulse crossing a tiny gap, a microscopic gap. It's called a synapse. Have you heard that word? I hope the biology teachers have. The idea of what's called synaptic transmission, that the signal changes from an electrical signal to a chemical signal. There's a tiny substance called a neurotransmitter that transmits the impulse onto the next nerve cell. So that's how all the system works. So even at the microscopic level, it is a chemical system as well as an electrical system. It's not like wires joined together in the same way as you have in an electric circuit. In terms of the overall structure of the brain, this model is generally considered these days to be an oversimplification. But I think it's quite interesting from a developmental biology perspective and an evolutionary perspective, if you accept that sort of view, that there are three areas of the brain which are associated with different sorts of activity. The brown area is often referred to as the reptilian brain. It's the area that you see, it's the part of the brain which is probably the most significant in reptiles, like snakes and crocodiles and that sort of thing. And it's the part that's concerned with basic responses, basic, fairly automatic things. So in us, it's involved in controlling things like balance and movement. It's involved in controlling breathing, sleep patterns, and lots of other things are in that part of the brain. And developmentally, that is considered to be the most sort of primitive part of the brain, if you like. In front of that, this thing called the limbic system. This is the bit that's really we're learning more and more about these days, because this is the part that we couldn't see before. We couldn't see if we were just looking at the outside of the brain, but we can see more of it now, that we're able to peer inside and particularly sample what's going on chemically inside this area. And the limbic system is associated with lots of things, but associated with emotion particularly, and is a site of memory, and is significant in a number of different ways in linking the two sides of the brain together. The bit that we know most about probably is the bit round the top. It's called here the neocortex, and it's the part that I'm sure you've all seen pictures of brains or even a real brain, and you've seen the what the surface looks like. It's highly fissured. It's got lots of little sort of cracks and marks in the surface, and it just covers over the top of everything that's in the middle in a human brain like that. I don't know whether you teach anything to your children about the brain outside of biology lessons, and I know in a number of schools in the UK they do things about the brain in terms of helping children to understand themselves as learners. If they're going to understand something about themselves as learners, then perhaps they need to understand something about the brain. And this sort of thing is done. I haven't got one with me, but one model for this sort of brain is to take your hand, make it into a fist, and then you can say, well, this part here, the wrist, and down the bottom here is the reptilian brain. This bit here is the limbic system. And then what you need, and I don't know whether you've got one, is something like a baseball mitten or a boxing glove, and you can put that on your other hand and put that on the top, and then you've made a model of the brain. This sort of triune model. This model is criticised. It is an oversimplification. These areas aren't quite as distinct as this shows, and they're certainly not those colours. That's just for the sake of making a difference between the three sections. But there's a sense in which this is quite a helpful model when actually thinking about what goes on in the different bits of the brain. So most of the sort of higher order thinking is in the neocortex, but we shouldn't ignore the other parts of the brain when we're thinking about how it works. Okay, we know a lot about brain structure. Again, it isn't really those colours. And I'm sure this is familiar to a lot of you. You've seen pictures like this showing these different lobes of the brain. So it's the front over this side and the back over that side. You've heard of some of these structures and what they do. That sort of picture of areas that are involved in particular senses, areas that are involved in what I mentioned about the reptilian brain and balance and coordination, memory and learning, areas that are involved in movement, areas that are involved in things like speech and personality, which are important there. And we've done a lot to map the brain, to know what different areas do. I wonder if you can make any sense of this. Have you seen a picture like that before? Or could suggest what it actually represents? It's not the left and right side. It's what it's trying to do. If I just go back a second, you see that area that there is called movement. There's a band down that blue bit which is responsible for a lot of muscle control in the brain. But the area that's involved in controlling some parts of the body, much bigger than others. So some areas are very small, some areas are very big. And those are represented in this this picture. It's called a homunculus. And what you see there are, well, most obviously, enormous hands. So what this is saying is there's quite a large area of that movement section of the brain that's involved in controlling your hands. Now, it's fairly obvious why that might be, because you've got very precise control over your fingers, and you need quite a bit of your brain to be able to do that. The arms are really skinny, aren't they, on that one? Why is that? Because actually, although they're quite big, your arms, there aren't many muscles there. You don't need a large area of the brain, as large an area of the brain, to control those muscles as you do the ones in your hands. What are the other areas that are big on there? Well, the eyes are quite big, but the mouth and the lips Why is that? Speech, because if we're going to speak, we have to have very precise control over the muscles in our lips and our cheeks and our tongue and our mouth in order to do that. So you can see there that the legs are quite small as well. The nose seems to have is quite large, and yet we can't move our noses very much. I'm not quite sure why that's quite as big as it is. Ears aren't very big because you can't do much with your ears. And I won't go into any further anatomical detail about that person there. But so the point is that as far as our mapping of the brain, we have quite detailed knowledge of how some bits work. We know how it works in terms of controlling muscles. We know how our senses work. But how do we think? And can we see thinking in the same way? Well, it's much more difficult, isn't it? Sorry, yes? No, but we'll come back to left and right later, because that's one of the areas that I think is quite interesting. These are just, to some extent, irrelevant facts. But you could ask yourself the question, is there any significance in any of this in terms of thinking about learning? There are 100 billion neurons. I don't know who sat down and counted them, but there's supposed to be 100 billion neurons in the brain. Is that important in terms of education, in terms of children's learning? Well, it suggests that there's a massive amount of potential there. Even, it was reassuring for me, that one of the neuromyths is that we lose brain cells as we get older. But that isn't the case. There is a process of neurogenesis, of creating new brain cells, which means that we don't actually, well, we might lose some, but they are replaced. So our capacity to learn is not reduced as we get older, even at my great age. Again, I'm not quite sure who did the calculation here, but this notion of being able to process, your brain being able to process something like 10 to the power 20 gigahertz, well, that doesn't really mean anything unless you think about something like a computer. And the most sort of sophisticated laptops these days, what sort of processing speeds are they up to? 8, 16, 32 perhaps? A fraction, a minute fraction of the processing power of the brain. All the things that can go on at the same time that enable me to be able to stand here, talk to you, look at what's on the screen, all those things happening simultaneously. So it's a fantastic processing speed. Mention this word synaptic transmission. We used to think that there was only really one important chemical substance called a neurotransmitter, which influence transmission across those synapses. But actually they've identified many of them, over 60 different neurotransmitters. Some of them actually allow nerve impulses through, some of them can block nerve impulses. And the effect of a lot of drugs, either recreational drugs or therapeutic drugs, is to interfere with the synaptic pathways and transmission. Is that important in terms of what we can think about with education? Well, it might be in terms of diet, in terms of the influence of chemicals on the brain. Later on it talks about bananas and chocolate. They're supposed to be good. And again, I apologise for not having brought lots of bananas and chocolate to the session, but they're foods that seem to have a direct activity, because they can, once they're metabolized, they can enhance the effect of the neurotransmitters and make the brain work better. The brain needs 25% of the body's oxygen supply. That's a lot, isn't it? So if we were in a sealed room And as we use up the oxygen within the room, we're going to find it more and more difficult to learn. We're not going to be in here that long, don't worry. So hopefully that won't be an issue. That might be significant. Certainly the final one on there about changes in synapse taking place with repeated stimulation. I think that is important. We know that if you do things over and over again, they go through a process of being what's often called automatized or made automatic. And that's quite interesting because there was a resistance some years ago within our system in the UK to what was often called quite dismissively or in a negative way rote learning. Do you know that term? R-O-T-E, rote learning. So it was traditionally associated with learning, doing things like learning spellings of words, learning multiplication tables, by reciting them over and over and over again. I don't know whether that's something that you did at school. It's certainly something that I had to do at school. And there was a sort of, at certain times during the 1970s, 60s and 70s in England, perhaps, that in primary school there was a move towards much more sort of pupil-centred approaches to learning, learner-centred approaches, and there was perhaps a feeling that doing that sort of thing was a bit too sort of mechanical, and we should get children to discover things more rather than be told them. And so rote learning went out of fashion for a while. It might have come back again more recently, but that notion of rote learning was seen to be something that was perhaps not a good thing to be doing. And yet, what's actually happening, or what appears to be happening in rote learning, is that you are reinforcing nerve pathways such that they become automatic. So in the same way as now, we can walk without having to think about it all the time, you know, our muscles just can do it automatically. We've learnt that, in effect, by rote, you know, by doing it over and over and over again. When we first started walking, we staggered around until we got the hang of it, and then we learnt to do it. The example that I often give about all of this is learning to drive a car. When you first start to drive a car, it's very difficult to manage everything, turning the wheel, working the pedals if you've got a manual car or even an automatic, and gears and indicators and looking in the mirror. And you do it all at a conscious level to start with. Then you pass your driving test and you start driving properly, and what happens? After a period of time, you can do it automatically. So what seems to be happening in neurological terms, in terms of what's happening in the brain, is that the initial learning in the front part of your brain, when you first learn something like to drive, is being transferred further towards the back, towards what's sometimes described as muscle memory, where things like walking and being able to drive and ride a bicycle and all those sorts of things are stored, so that they're there in a very highly consolidated form for you to be able to access at any time. It's no good if a wild animal appears through the window having to think, I need to run now, and that leg goes in front of that leg. You've got to just move, haven't you? So the further back in the brain these things are, the better. So, you know, just a little thing like that can actually have quite significant influence on the way that we think about processes of teaching and learning. Okay, I mean, there are lots of things we could talk about here. You know, the brain needs water to work. You've got water bottles in front of you. We know what effects dehydration can have. We know what effects that we shouldn't drink too much tea and coffee and Coke, because that's got caffeine in it, and that's diuretic, and it takes water away from the brain. So, you know, implications of that are fairly obvious. One quite interesting thing is this relationship between levels of stress and levels of performance. And by performance, I don't just mean in a test, I just mean any sort of learning, thinking sort of activity. Sorry, you've got a question. You want to answer the question? Go on, answer the question then. A moderate level of stress, yeah. I mean, just first thought about that might be, well, if levels of stress are high, then you would expect levels of performance to be low. If you're really stressed, you're going to perform low. So therefore, you might say, well, if levels of stress are really low, then performance is going to be high. But there is evidence to suggest that actually the curve looks something like that. And biologically, if our stress levels are really low, human beings are a bit like other animals, and our natural desire is really just to go to sleep. You know, if there's no pressure from outside, then the brain wants to shut down and the body wants to go to sleep. Stress levels are too high, yes, yeah, you become very anxious, stressed. You can't learn. And biologically, I mean, that inverted U relationship seemed to be associated at the low end with low pressure boredom, high pressure anxiety and unhappiness, and so there's a sort of an area of best performance where there's a moderate amount of pressure. So thank you very much for colleague at the back for that, an optimum level. What's actually happening here appears to be that if particularly high levels of stress, blood flows away from the front part of the brain, which I said is the most advanced part, and goes towards the rear. So this idea of fight or flight, you know, if there are high levels of stress, what do? Do you run away or do you face up to it and attack? But if the blood has flown away from the front part of the brain, and the front part of the brain is the part that you need in order to think, then you can't think. So I would suggest if you can't think, then learning is going to be problematic there. So trying to get the right level there, trying to get there to be some pressure, and we often talk about the balance between support and challenge. So we're providing activities that are sufficiently challenging to keep up a level of stress, but we're providing support to learners to make sure that they can cope with it. Okay, I want to talk about this notion of brain-based learning. Is that a term that you've come across? Yeah, some of you have heard that term. One response to that statement is, well, for goodness sake, all learning is brain-based. You know, how could you have non-brain-based learning? Well, the intention of the term here is to suggest that there are certain things that you can do, certain sorts of learning, that are grounded in neuroscience research, and that if you do them, then your students, your children will learn better because it's grounded in something that we can show about how the brain works. So I'm going to just give you a few examples of this, and then I want you to think about these questions. What's the theory behind the example given? I mean, is there any theory? And if there isn't any theory, does it matter? If something seems to work, do we do it without worrying too much about what's behind it? Has it been tested? And then is this something that you do or would do? So just a few random examples. Do you use mapping techniques with your students? Now, this is an example of a mind map. It's a mind map about the brain. And there are rules about mind mapping, about using different colours and different ways, different conventions for showing things, how things relate to one another. The suggestion is that actually a two-dimensional mapping might be more helpful than often the way that children's learning is made very sequential and linear. And yet that doesn't seem to be how information is stored in the brain. It's not stored in, I don't know what sort of image you have about how the brain works and how information is stored in it. And the old image used to be the filing cabinet, but we don't have filing cabinets anymore, do we? So, but the idea of a nice neat set of drawers with dividers in, and all the knowledge is nice and neatly compartmentalized in there. It appears as though it's stored in a much more sophisticated and complex way that allows very complex interactions between the information that's stored. So mapping techniques could be argued to be brain-based. That could be an example of brain-based learning. Now if you explore this, there is quite a lot of evidence. The mind map was in, I don't know if it was actually invented, but it's very often associated with a guy called Tony Buzan. Buzan, have you come across that name before? He certainly developed that idea and marketed it before, but there are other techniques like concept mapping, which others have developed and presented, which actually are sort of metacognitive tools. They help children to think about their thinking and learn about their learning. So they're quite powerful in that sort of way. And there is some basis, brain-based basis for that. This is, I think this one's quite interesting from the point of view that it's been known about in psychology for a long time, since the 1920s or even earlier. But before we actually knew how the brain worked. But there's now some evidence from neuroscience that there is something in this, and it's called the primacy recency effect. And what it says is that in any activity that you do, like a lesson, which has a fixed length of time, that we start off really well at the beginning, but our concentration levels drop as we go on. And we end up with something like this. You know, concentration levels drop. But the interesting thing, that's the primacy bit is the beginning. The recency bit is, as we come towards the end of the time, if we know when the end is, so we know that this session finishes at 8 o'clock tonight, isn't that right? No. 5:15. This session finishes at 5:15, so as we get closer to that, then your attention picks up. So that's the net effect. There's a droop in the middle. And so the learning would be seen as being, in effect, the area under the curve. So it's much reduced in the middle, you know, the amount of learning that's going on there. Right, but by putting breaks into a lesson, and this might be just something that you do intuitively without thinking, well, there's a brain basis for this, that you can't stop there being little droops, you know. I'd argue even the most charismatic speaker, and I really was listening to every word that Alan November said in his keynote this morning. I thought that was fascinating. But no matter how hard you try, there is a tendency towards a bit of a droop. But if we break things and we do something different, maybe it's a water break, a change of location, a change of activity is the usual way of doing this, then we can reduce the big curve, and you can see that the area under the curve now is a lot larger. There's a lot more learning going on if we do something like that. The example I put in there, the other example was there, I'm going to come on to in a second, is Brain Gym. And I don't know whether you've heard of that or not. Okay, so that's the primacy recency effect, which has been known about for a long time. Psychologists talk about this. Serial position effect as well, it's called, and that's, if there's a link in the PowerPoint that will take you to something that gives a bit more information about that. It's quite a simple thing. It's something that's fairly easy to do, but there is actually some neuroscience evidence now that this actually does make a difference. You know, here's a bit of brain-based learning. Chewing gum is good for the brain. Do your students chew gum? Possibly not in your lessons. The interesting... Sorry? Right. I mean, some people believe that it aids concentration. This was a study that was done. Ironically, I read about this just as I was on my way to do some teaching in Singapore. And Singapore is a country which has more or less made chewing gum illegal. You can't chew in the street. If you drop chewing gum, then they imprison you almost. So there I'm reading here, well, actually, no, chewing gum is good for the brain. And I think this is quite an interesting example because it's suggested chewing gum can improve. The headline is good for the brain, but actually the detail of it then says long-term ability to remember words. That's a very narrowly defined type of activity. So is that really good for the brain? It also improves short-term memory. Did nothing to help concentration, and as yet there's no definite explanation for the results. So do you remember my questions before about, you know, what's the evidence base for this? What's the theory? What's the evidence base? And would you do it? I think that's interesting compared to this one. It goes on to say a result with glucose tablets were even more striking. So perhaps it's nothing to do with chewing gum. It's actually to do with something else. Chewing the glucose tablets might have an equal effect. Maybe just chewing raises the heartbeat, produces insulin. Both of those things enhance memory. So that could be the explanation for it. But we've got an observation that is extrapolated. Now we go further from an observation to actually coming up with some idea of saying, well, chewing gum is good for the brain, and then perhaps, well, we should be allowing children to chew in their lessons. Don't go away saying that I said that, because I didn't. Just look at these colours for a second. How did they make you feel? Did you feel that you were able to concentrate more with the green one? Did you feel calmed by the blue? Did you feel energized by the red? It suggested that colour has an impact on learning, and there are some commercial organisations that offer educational services to schools to provide appropriate colour schemes for the classroom. Apparently bright colours, primary colours for primary schools, more subtle colours for older children. How are we going to go about that? I mean, I think in most classrooms, sometimes you want your children to concentrate, sometimes you want them to be a bit calmer, sometimes you want them to be a bit more energized. Perhaps we should have, I believe you can get them, it's possible to get panels which are connected up somehow to electrical device that will change the colour of the panel. So perhaps you should have a switch on your desk as a teacher where you can change the colour of the walls in your classroom in order to produce a certain sort of mood. You know, I'm not convinced about this. It may be that there is a little bit of evidence that those colours, actually seeing those colours, does actually have an impact on the brain. You can use an MRI scanner to show somebody different colours, and you can see different activity in the brain. But to go from that to saying we should paint classrooms a certain colour seems to be, again, I use this word extrapolation, going further than is justified perhaps from the evidence. Okay, brain gym. The theory proposed about brain gym, if you just Google it and look it up, it's a suggestion that by doing certain sorts of activities, you can promote the connections between the left and right sides of the brain. Yeah? Do any of you do anything like this in your classrooms?
It's become a business here in Jordan.
It's become a business, colleague at the front says. Yeah, I mean, it's a business in lots of parts of the world. People offering services, offering training courses, and so on. I don't want to upset anybody who's bought into that, but I'm afraid the evidence is rather flimsy that it is actually grounded in good neuroscience. But let's give it the benefit of the doubt and let's just try something. Please cooperate with me now. I need you to all stand up. Thank you. I'm going to show you the alphabet. I'm sorry, this is in English. I'm going to show you the alphabet, and underneath the alphabet are 3 letters, either an L, a T, or an R. Right, what we have to do is we have to say the alphabet all out loud together, starting from A, and if it says L, we hold up our left arm, okay? If it says T, we hold up both arms together, the T is for together, and if it says R, we just hold up our right arm, okay? And we just do that for all the letters, so each letter, as we go, we're doing 2 things at the same time. We're saying the letter, and we're doing this physical activity with our arms. Now, I'm hopeless at this, so I'm now going to stand at the back whilst we do this, so you can't see me. I'm going to do it, but I get it wrong, and I don't want to distract you. Okay, so I'll start us off. Right, ready? A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Thank you very much. Apologies for speeding up towards the end. Did you feel the left and right side of your brain working better together because you were doing that activity? I didn't. The evidence for that is quite shallow. The whole thing about the left and right sides of the brain is a problem anyway, and I'm going to talk about that a little bit later on. Is that something you might do in your classroom?
Maybe as a break.
Well, I mean, going back to our primacy recency thing, you know, well, what it might do is just create a break in the lesson so that we avoid one of those, you know, big droops, but cut something down. It could, well, I feel a bit invigorated by doing that. You know, we had to get up, we waved our arms around, our blood circulated a bit more blood to the brain. That can't be a bad thing, can it? So it's not doing any harm. It could do some good, but the evidence that it actually helps the connection between the left and right sides of the brain is very flimsy. So I think that's something to just think about. So I'm not saying don't do it. In fact, I think I'm probably saying there could be a reason for doing it. But I'm not claiming, and I think it's very hard to claim, that it has that sort of impact. Another part of this brain-based learning, and a big part, is this notion of what's often referred to as the Mozart Effect. And there's a link in the PowerPoint to a website that will say something more about that. We know that music has an impact on us. One of the reasons why we listen to music, most of us, is because it has an emotional impact. It can soothe us, it can energize us. I find music has an effect more than colour on me in terms of being able to concentrate. I work with music in the background. But this idea of the Mozart effect is going a bit further. The suggestion is, well, several suggestions about what's actually happening. But the suggestion is that music like by Baroque Western composers like Mozart, Vivaldi, a lot of it is at a rhythm of about 60 beats per minute, which is associated both with our heart rate, our natural resting heart rate, for younger people than me perhaps, but also brain activity, that it's associated with, it's often called alpha wave activity in the brain. And there is some empirical basis that some students in about 1930 were played a Mozart piano concerto, and they were able to learn more words. It was a vocabulary test. They were able to learn more words when they had the Mozart played to them. And from that, this whole, it's another industry. I don't know whether you've had this, but you can buy CDs and get MP3 music of different things that are supposed to follow this Mozart effect. But again, it's been extended wildly beyond that to lots of other different sorts of music. And I think particularly in our context here, there's clearly a cultural dimension to it. Now, should you be playing your children Mozart? Are there other more culturally appropriate musics to play them? Does Mozart have the same effect on children working within the Arab world or the Chinese world as it does to children in the West? So we know there are lots of things we can use music for, and I'm not saying people shouldn't use music in the classroom. I mean, a number of you possibly do. Do you play music at all during your lessons? Yeah? 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 So I'm not saying don't do it, but I'm saying don't think that this is something that really has a, if you're playing Mozart, your children will learn better. I don't think the two necessarily follow. This is a rather weird one. If you ask somebody a question, if they look up, they're visual learners. So if you ask them a question, if you watch what happens to their eyes when they respond, the idea is that if they look up, they're visual learners. If they look side to side, they're auditory learners. They look down, they're kinesthetic learners. And if they look straight at you, either the question was too easy or they're not telling you the truth. So we're now getting into a rather delicate and dangerous area, because I'm using these words visual, auditory, kinesthetic. V-A-K. Have you heard those letters used before? The VAK, V-A-K. visual, auditory, kinesthetic. There is an awful lot. This is one of the really big things that's supposed to have come out of brain research that is about learning styles and is about trying to identify learners as having a particular way of learning. We have visual learners, we have auditory learners, we have kinesthetic learners. And there are various sort of tests and inventories available to look at that, but this system is perhaps a little easier. You just ask a child a question or an adult a question, you see how their eyes move. They obviously don't need to know that. They can't know what you're looking for. But if they're making an honest response. Now that sounds a bit weird, doesn't it? But actually, this is one thing that it does appear as though there is a neurological basis for the eye movement associated with these what are called learning channels. Now, I won't go into it in detail, but there is something called neuro-linguistic programming, NLP. I don't know whether you've heard of that. It's a bit of a mystery, NLP. It's one of those things that there's a degree of secrecy about it and about learning what the foundations. The people who have developed NLP programs don't want to give away their secrets, and so you have to buy into this and almost sign something to say that you'll never share the secrets with anyone else to really get into NLP. But part of NLP, and it's a sort of therapeutic and counselling thing, really, but part of it is to do with the way that we do take in information. And that term that I use, learning channel, the way that information goes in through our eyes, through our ears, or through a more sort of bodily, physical interaction with the environment, that is something that there is a lot of clear evidence for. But the VAK movement has done this extrapolation process. It's taken something that there is some evidence for and extended it beyond a point which is reasonable. And so what happens is that you move from saying this is a learning channel preference, it's the way that you take in information, to saying that that has some sort of more general influence on your learner, such that you would label a student as being a visual learner, and you would think you would need to treat that student differently from a student who's labelled as an auditory learner or a kinesthetic learner. And there are people around who are promoting VAK who would say that, and I don't think it's quite as extreme now, but at one point certainly there were people who would say, well, you should put all your visual learners together in one group, and all your auditory learners in one group, and all your kinesthetic learners in one group, and you should give them different experiences. Now, that isn't what VAK is about. That's going beyond what it's about, and coming up with something which is labelling students. And rather than thinking, well, actually, if this child has a preference for visual learning, what can we do to help develop their other sorts of learning? And I think a lot of people now are taking a much more holistic view about this, rather than one which is labelling and segregating students. Sorry, I just need to go and look at the time. We're not going to do this because it involves too much physical activity. But this is a sort of related thing, which, as you read it, I don't know whether you feel, what? This sounds very silly. there's a suggestion, and it comes out of that VAK sort of orientation, that if you want to learn something, it's better received from the right. So if you, if I want to tell you something, I should come up to your right-hand side rather than your left-hand side, okay? And I should give you the information in that direction. This is another one of these left-right brain things. If you want to express something, it's better done to the left. So if you want to feed something back to me, it's better that if I'm on your left-hand side. So I've been over here, but now, and I've said something to you, but now I've got to go over here for me to get it back from you. So when talking to a pupil, be on their right side if you want to give an instruction, be on their left if they're expressing an idea. Ask a question on the right, receive the answer on the left. If you want to learn a spelling, hold it up to the right. If you want to say it, do it to the left. There's far too much... Sorry? So I need... Yeah, right. Sorry, I was a bit slow there. So I'm... it's going to be good for me because I could do with losing some weight. So I do need to keep moving backwards and forwards. But it's a strange thing. And some of these things, you know, are being presented as though you will do them because somebody says this is grounded in neuroscience research. And I don't think you would be quite as silly as that. But it's just an example of some of the more crazy things that we're being told we should do because it's more in sympathy with the way that the brain works. So we come on to this notion of neuromyths. I've used that word, these are popular accounts of brain functioning which often appear within so-called brain-based educational applications. And in the reference to these quotes, the author says, this is not to say there isn't a glimmer of truth embedded within various neuromyths. Usually their origins do lie in valid scientific research. It's just that the extrapolations, so that's my word from before, go well beyond the data, especially in transfer out of the laboratory and into the classroom. So that's what we mean by neuromyth. There's a reference in the PowerPoint that will take you to that paper if you want to follow it up. 3 common neuromyths. We only use 10% of our brain. That's one that seems to still be persistent. May have been suggestion here, or in fact in that paper that I just quoted from, is it may have developed from early research stating only 10% of the brain was known about, or later studies showing not all of the brain is active at the same time. But the notion that we don't use all of our brain is a rather strange one, certainly not supported by neuroscience research. We lose brain cells every day and eventually they just run out. I've talked about that one already. You can't change your brain. Well, we're getting into another quite dangerous area here about intelligence and notions about intelligence being something that is fixed rather than something that can be developed. And our brains are constantly changing in response to experience. And this notion of plasticity, we know from people who've had brain damage from strokes or accidents or whatever, we know how the powers of recovery of the brain are enormous and terrific. Sorry, I've just realised that if I keep moving around, then I've got a cameraman at the back following me. So I'm making his life more difficult by me jumping around. I'm going to come back over here when I'm slightly more comfortable. Learning styles, VAK, is certainly something that would be put into this category of neuromyth. I don't know that you can actually read the right-hand side of the paper there, of the slide, sorry, but when you get the PowerPoint you can read what somebody who's working in neuroscience and education at Bristol University in the UK said about this particular belief. But I'm going to show you just a short video clip now so that you don't have my voice all the time. So we're going to an American psychologist called Daniel Willingham, and as you'll see, this is a YouTube clip. So it's about 5-6 minutes long, so we'll just see what he has to say about this idea of learning style.
Hi, my name's Dan Willingham. I'm a cognitive psychologist and a neuroscientist.
Sorry.
At the University.
I hadn't appreciated it wasn't on the screen. Technologically inept. It's okay. I just need to close that down. It's fine. I'm there. Right, he's there.
Virginia. I'm going to talk to you today about learning.
Yeah.
Hi, my name's Dan Willingham. I'm a cognitive psychologist and a neuroscientist. I'm also a professor at the University of Virginia. I'm going to talk to you today about learning styles and how cognitive psychologists know that they don't exist. Now, the basic idea of learning styles seems to make a lot of sense. The idea is that different people have different ways of learning. So if you can teach in a way that's consistent with a student's style, he or she should learn better.
There have been lots of these proposals over the years, like verbalizers versus visualizers, or analytic versus non-analytic thinkers. I'm going to talk about what is the best known, visual versus auditory versus kinesthetic learners, but what I'm going to say about this theory really goes for all the others too. So what are learning style theories? The idea is that the way that information is organized, or the way that you think about it, matters in how easily you understand or learn it. Suppose you're building a new house and you're trying to give your friend a sense of what it will be like. The visual learner will understand best by seeing the plans, the auditory learner by listening to a description of the house, and kinesthetic learners need to move, so your kinesthetic friend might build a model. The theory says that anyone can learn in any of the three ways, so the mostly visual person can still learn auditorily or kinesthetically, and likewise for the mostly kinesthetic person. But the brain doesn't work that way. It is true that you can store memories in any of those three formats. Suppose I ask you, what's the shape of a German Shepherd's ears? Most people say that they look at a visual mental image when they answer that question, and there is good evidence that you do indeed store that information visually. Or if I ask, who has a deeper voice, your best friend or your boss? You'll sort of listen in your mind's ear, and those sounds are stored auditorily. Kinesthesia is a little trickier, but it works the same way. Movements that you know really well, like riding a bicycle or tying shoelaces, will be stored kinesthetically. And yes, it's probably true that some people have clear, vivid images, and some have weak, undetailed images. Almost any characteristic of people is going to vary, whether it's height or weight or visual memory. So in that sense, some people are good visual thinkers. Okay, so that's the scientific background, and it sort of sounds like the theory is right? Let me tell you what's wrong. Think about what the theory ought to predict. Here's a visual learner, and here's an auditory learner. Suppose I give each of them two lists of words to learn. For one list, I read it aloud, auditory presentation, and for another list, I show a series of slides, a visual presentation. Later, everybody gets a test. The prediction is straightforward. The visual learner should learn the slides better than the words, and the auditory learner should learn the words better than the slides. Lots of people have done that experiment, and that's not the result you get. The thing is, you don't learn the words visually or auditorily. Actually, an auditory test would be about what the particular sound of the voice was, the auditory quality. For example, did you hear shell or shell? And a visual test would be for the particular visual qualities of the slides, what they actually look like. When you just ask people to remember the words, you're really asking them to remember meaning, not sound or visual information. And in fact, most of what teachers want students to learn is not visual or auditory or kinesthetic information. It's meaning-based. For example, you know what the word opera means. For you, that's a meaning-based representation. And the meaning is independent of whether you learn the meaning by first seeing an opera or hearing an aria. Most of what's in your head, especially what you learned at school, is meaning-based. So you might think, okay, but the visual, auditory, and kinesthetic idea is still right some of the time, like when teachers want students to learn things that are not meaning-based. It's true, sometimes students might learn things that are essentially visual, like the shapes of countries on a map, or something that's essentially auditory, like a correct French accent. But notice what the theory's prediction would be. The prediction of the theory is not simply people with good auditory memory will be better at learning auditory stuff than people with average auditory memory. No one would argue with that. The prediction is that an auditory learner is always going to learn better if you present things auditorily, because that's supposed to be his or her best modality. Well, that's pretty obviously silly. You're not going to try to come up with an auditory presentation of the shape of Algeria. Everybody needs to see it.
Okay, so let me summarize what I've said so far. It's true that some people have a better visual memory than other people, and other people are better at learning auditory material than other people are. But that fact isn't really all that important for teachers, because most of what teachers want students to learn is not particularly visual or auditory or kinesthetic. Most of what teachers want students to learn is based on meaning. The second point concerns the particular prediction of the theory. The important prediction of the theory is not that some people have better visual memory than other people. The prediction is that those people with a good visual memory will always learn better if you present things visually. But that idea is clearly wrong. When you've got something that you want students to learn that's especially visual, like the shape of a country on a map, everybody needs to see a visual presentation, not just those people who have really good visual memory. Okay, so if the theory is wrong, as I'm claiming, why does it seem so right?
One reason is that everyone believes it, not just teachers. The theory is accepted by about 90% of the students at the University of Virginia. Second reason people believe it is that something close to the theory is right. People can learn in different ways, and some people are especially good at learning certain types of information. But the specific predictions of the theory and the way that you would apply it in the classroom are wrong. A third reason this theory seems right is that if you already believe it, you'll probably interpret ambiguous situations as consistent with the theory. For example, suppose you're talking to a student about the structure of the atom, but it's not really clicking. Finally, you say, picture the solar system. The nucleus of an atom is like the sun, and the electrons are like the planets spinning around it. The student understands, and you think, aha, he must be a visual learner. But maybe that was just a good analogy that would have helped any student. Or maybe the student needed just one more example for the idea to click. Why the student understood at that point is actually ambiguous. But if you already believe the theory, you're likely to interpret what happened as being consistent with the theory. Remember, there are many theories about learning styles. Visual, auditory, and kinesthetic is just one. But what I've said about that theory goes for the others too.
Good teaching is good teaching, and teachers don't need to adjust their teaching to individual students' learning styles.
Okay, there's quite a lot on Daniel Willingham's website, which you might like to have a look at in your own time. So we'll just get rid of that. Back to my... So that one is one that I think we need to look at carefully, and I know at the same time as I'm doing a session here, someone else in another room here is doing something about VAK and learning styles. I'm just saying what others have said about that. I wouldn't want to go any further in terms of saying there's anything that we shouldn't do. I don't think we're going to do any harm to our learners by exposing them to these sorts of ideas. But if we're trying to encourage others to use them on the basis that there's a neuroscience foundation to it, then we need to check that there is a sound foundation to it. One of the other persistent neuromyths is this notion about left and right brain. The notion that the left brain is all about reasoning and logic and the right brain deals with everything creative. Research shows all parts of the brain are involved in those sorts of activities. The diagram at the bottom is taken from a book about something that was called accelerated learning, and represents this neuromyth. These things on the right brain and on the left-hand side of the brain are the logical reasoning things, and things on the right-hand side of the brain are the more creative things. Now, I don't think, so we're back to brain gym. If it can help link the left and right sides together better, then we can have a more holistic sort of view of learning. And yet, this lateralization theory doesn't work. There isn't the evidence for it. In the right and the left sides of the brain, there are slight differences between them, but certainly the really important thing is that the two sides can work together as effectively as possible, and I'll come on to that in just a second. There's a link in the PowerPoint to a publication from a few years ago about neuroscience and education that was done in the UK, and talking about a UK situation there. They're saying education has already invested a vast amount of time and money in brain-based ideas that were never based on any recognizable scientific understanding of the brain. Many ideas remain untested, others are being revealed as ineffective, and that we need an improved dialogue between neuroscience and education to really develop things that are sound and that are going to have impact. My analogy is taking the pharmaceutical industry and the way that drugs are developed. What happens is that there is an observation or a discovery of a substance that seems to have some therapeutic effect that will cure a disease or treat the symptoms of a disease. So what happens? Well, we go through a process of experimentation, of trying it out and just making sure that it was due to that substance and not due to something else. Possibly that's done on animal trials, or possibly in other ways these days. Then we go on to clinical studies. Once we're reasonably happy that it's not going to do any damage to anybody, then we start giving it to people. We do clinical studies to larger groups of people to see whether it actually has some impact. And only then, in our system, will it be approved. There's an approval process, the drug is released, and doctors can start prescribing it to the general population. But there's still a lot of monitoring goes on to make sure that evidence is being collected about impact and that there aren't any side effects and so on. Now, I think the same, if we apply the same model to this neuroscience research and this notion of brain-based learning, I think we're on level 1 or 2 here. I don't think there's anything that's got through to anything equivalent to level 3 of a clinical study. The closest I can get is to some work that's gone on in what's called cognitive acceleration, trying to develop children's thinking abilities, where there is quite good systematic research evidence about that you could say is approaching level 3. But mostly we're level 1, sort of getting into level 2. And so that danger of taking things and applying them, knowing that they work, is not the stage we're at the moment. And I'm sorry, I realised by this time we might have some disappointed people in the audience who are hoping I was going to tell you lots of new things that you could be doing. I think it's much more a case of looking at what we're doing at the moment and seeing how that fits with what we know, and waiting for these wonderful new discoveries, if they ever come along, to help guide our practice. But we're just not there yet. This is from that same report. 90% of teachers that were surveyed for this study thought that a knowledge of the brain was important, and that we should try to build in brain-based learning if we could, if we knew what that was, and that we needed to have a dialogue about that. This was a document for schools in Scotland. Scotland's part of the UK, but has traditionally always had quite an advanced education system. And this is the advice they were giving them. And you can see they've said providing visual, auditory and kinesthetic ways of learning. Perhaps they don't go very far with that, and perhaps they're not going any further than Willingham says is acceptable. But they have picked out mainly things which we can say have some influence on the brain. But it's not perfect, but it's almost there. Just to finish off a little bit, I'm interested to see how new ideas from neuroscience do relate to existing sort of theories about learning. And I don't know whether you've studied Piaget. Aware of the psychologist Piaget and his stage theory? I mean, that was developed years and years ago, well before we had all this knowledge about the brain. And yet, there's a link I can see between what Piaget calls formal operational thinking and what seems to happen in the brain in this process of myelination that I mentioned right at the beginning. This myelin protein coating the nerve axons makes the nerves conduct impulses more efficiently. This could explain why myelination going on in adolescence actually enables children to think in a qualitatively different way from the way they were thinking before, and could be, a neurological explanation for what Piaget pointed out from a psychological point of view. That's a good thing. What goes on in the brain during adolescence? I mean, somebody has actually gone so far as to suggest that we should really abandon education for children between the ages of, about 13 and 16? Because there's too much going on in their brains. It's being rewired. There's a lot of hormonal influence, chemical influence on the brain during that time, both for boys and girls, which means that learning is very difficult. And one book talks about the brain being closed for construction during those years. But I don't think it's going to be very popular politically to say, well, yes, we should shut schools down for those 3 years. What do we do with the children? I don't know. We have to sort of lock them up stop them running wild, but we shouldn't try to educate them. And yet this is the time when we have the greatest expectations of them and the most fundamental sort of decisions for many children about their future education. I mean, the last example, starting to get into the dangerous area of whether there's a difference between male and female brains. There does appear to be a difference in terms of the development of a structure called the corpus callosum. This is a yellow body in the middle of the brain that links the right and left sides together. And it seems to be, the development of this structure seems to be enhanced by the hormone estrogen. Obviously, girls have got a lot more estrogen. So I said it's tempting to offer this as an explanation for why girls mature earlier than boys, because estrogen is actually, by mature, we're saying that they think more rationally, logically, they can perform better. And so maybe there is a neuroscience explanation for why that might be. I'm not going to go any further into any differences between male and female brains, but certainly again there's an area where there are some people that are trying to say, you know, boys' brains are different to girls' brains and that we should treat boys differently from girls. There isn't the evidence for that at the moment, certainly not any evidence that has been tried out in the way that I've just described. There's a lot of resources available on all of this. There's some websites that it's worth having a look at. Most of the ones at the top are from the UK and the US. There's a very good report from something called the Education Endowment Foundation. And you can obviously Google these things or get the links from the PowerPoint when it's available, which is a UK foundation that did a report about education and neuroscience fairly recently, and the UK Royal Society did one as well. And there are quite a lot of YouTube clips that are linked in to the PowerPoint as well. Okay, that's the end of what I've got to say. Could I just ask, before we finish, has anyone got anything else that they would like to offer as something that they do that they recognise has got or would think has got a brain-based neuroscience sort of basis to it? Have I talked about the sort of things that you do? Yeah, sorry. Right, okay, so, okay. Yes?
I have a question. Since these are neuromyths, why haven't neuroscientists been more active in the educational field to promote things that are evidence-based? What stops them being?
Because there are very few neuroscientists who are actually working in education. They're working in neuroscience, and their main concern is to understand how the brain works. If other people want to take their research and try to apply it in the classroom, they haven't got the time to really devote to that. There are only a few places where there are centres being set up now for neuroscience in education. There's one of them in the link on the PowerPoint, where they are actually trying to get neuroscientists and educationists together and think about this. But it's a very long-term thing to actually be able to collect the evidence of impact that would really be convincing to enable us to stand up and honestly say to people, this is something that you should do because it has got a basis in neuroscience. There you go. Yeah, I mean, there's some evidence that new treatments for things like Parkinson's disease are going to enable this natural process. It's that the disease is suppressing a natural process. So if we could stop that, then even in those people, the neurons, we could get neurons to grow. Okay, are we up to time? Yeah. I don't want you to feel shortchanged because I finished early, but it seems to be exactly 5:15, so that's perfect. So thank you very much for listening. Hope you enjoyed it. It's some use. Thank you.